See here that we've got our starter file, and it's labeled FAM7340, which is the gene that we're working on. And the first thing we see is something that looks like this, all these pink bars and a lot of different other colors. So what this is showing is the different groups of genomes and where their start sites are. So this is explained on page 60 when it comes to the how to use Starterator. These you can the left bar right here represents the stop codon from the previous gene, and then all of the potential start codons that can be used. The start codon that is used the most often is going to be in green here, so it's going to be number 10. Now, personally, I don't care for using this visual because it's kind of difficult to figure out. I typically go down to the next page. It's going to give you the FAM report. It's going to tell you that there are 53 members, so there are 53 different genomes that have been annotated that have this particular gene. 26 are drafts, so about half of them have been annotated, half of them have not been annotated yet. And which phage is in which track is down here. So you can see Octavius rex is right here. It's in track 5. So what that means, and there's all these other phages as well. So it means all these other phages have the exact same sequence as Octavius rex, all the ones in track 5. So go up to track 5 here. It's going to be 1, 2, 3, 4, 5. So this is the track with Octavius rex. And you can see all the potential start sites. And the one that's called is going to be in green here. Now, if you go down below these, it's going to tell you what the most what the start number was most commonly called. And this is start number 10. So of the 27 genomes that have been annotated, start number 10 was called in 21 of them. So what we want to do is we want to go down to our Octavius rex genome information in Starterator and see, is track 10 in, or is start number 10 in this particular genome? And if it is, does it match up with what our other, what our DNA master called? So in our Starterator report here, we can go down, and I actually am going to search Command F, and I'm going to search for Octavius rex. And there's going to be a section that's just for Octavius rex. And here you can see it's going to tell us that the start site for the draft annotation was 1888. The stop was 3402. This is gene 3. And in fact, start site number 10, which is the most commonly called start site, is present in Octavius rex, and that is at nucleotide 1888. So if we go back to DNA master, we'll see that is what our gene prediction program is called as well. So what this is telling us is, that the most commonly called start site is this particular start site. Our gene has this start site, and this was the one that was predicted by the prediction program. So if we go back to here, the question is, they don't really have a question here, but the question would be, does Starterator support the called start site? And the answer to this is yes. Starterator supports start site at 1888. And we can also, it's helpful to look at the FAM report and look at the two genomes that we're comparing it to. So Frosty, for example, 24. I'm going to go to the section just for Frosty 24. Right here. Also has the same start site. And Gomashi. So these are the ones that we compared our genome to in Famarator. Also has start site 10. This is at 1889. It's off by 1 nucleotide. So pretty close though. So this is increasing, this is even more evidence that this is the start site that is correct. So we've looked at Starterator, and this probably didn't make a whole lot of sense to you. Starterator is very, it's kind of a confusing program at first. We will talk more in class about how to use Starterator, but I just want you to start looking at this particular section. Again, on page 60 and 61, there is information about how to use Starterator, as well as there's a little bit of information here on page 73 about the best way to use Starterator. So we took the Famarator map, we identified the FAM, we looked at the top start site, and we found that the most commonly used start site is in fact in our gene, and it's used by the other ones that are very similar. The last piece of evidence that we want to look at is what's called the ribosomal binding site. Sometimes this is called, so this is RBS, sometimes it's called the Shine-Dalgarno site, or SD. So in order to understand what this means, I'm going to show a few things in PowerPoint. So the central dogma, remember, says that DNA gets transcribed into RNA, and that RNA gets translated into protein. So in order for the RNA to get translated into protein, the ribosome, the protein complex of the ribosome, has to take this RNA and translate it into protein. And it needs to know where to bind on the RNA to start this process of translation. So the ribosome physically binds to the RNA to translate the protein. I'm not going to show this video. I would recommend that you take a look at it, take a break from this video here, take a look at it. This gives you some background on how translation works. So you can type in this address. Now, in prokaryotes, so remember this is based upon how translation works in bacteria because the viruses are doing all of this in bacteria, the ribosome binds to the sequence that is upstream of the start site. So what we're doing in each gene is we're trying to find which start site is at the beginning of each of the genes. The ribosome binds upstream of this in this ribosome binding site, or the Shine-Dalgarno sequence. We like to look at how close is this sequence to the start site. Turns out distance of about 10 to 12 nucleotides is ideal here. And what this sequence is also is quite important. So the Shine-Dalgarno sequence is this AGG, AGGU. It's a purine-rich sequence. And you notice there's a different sequence up here. The reason this is a different sequence is because the Shine-Dalgarno sequence can differ a little bit, but it tends to be about 10 nucleotides upstream of this first codon. This is where the ribosome binds. So we do like to look at where is a sequence that matches up with this ribosome binding site. This influences, where the sequence is influences where the translation starts. So a way to think of this is, let's say this is your viral genome. So we've got, this is kind of how you would look at the frames window. So if we go back to DNA Master and we opened up the frames window and showed the open reading frames, so you have 3 frames up here, 3 reading frames up here, 3 reading frames down here. You can see the genes are very close together here. This is very close to this, and they're on different reading frames, and sometimes they're on even different strands. We'll focus on the ones that are on the same reading, or the same strand right now. So let's say you have these genes. Now keep in mind, this is only one stretch of DNA. And don't worry about the actual sequence. This is just, what I'm trying to show here is you have these genes that kind of are very close to each other, and oftentimes they actually overlap. And these are oftentimes bunched together in what are called operons. So many genes get transcribed together, but they all get translated individually. So even though you may get all of these genes in one RNA, they all make separate proteins. So when we look at this in the frames window, it's like this, right? And each of these is going to begin with a start codon, and that's what we've been annotating. And I'm just going to focus on these 4 right here. And each of them end with a stop codon. So this has a start and a stop, this has a start and a stop, a start and a stop, and a start and a stop. But keep in mind, this is still just one this is one DNA sequence. They're just in different reading frames. There's only one genomic sequence here. So even though we look at this in the reading frames like this, it's actually like this. These genes are overlapping oftentimes. So there are these ribosomal binding sites that are upstream of each of these start codons. And these ribosomal binding sites, or also known as the Shine-Dalgarno sequence, these are oftentimes in the gene that is upstream of it. So what we're looking at, this last bit of data that we want to look at, is what is the distance between the ribosomal binding site and the start codon in each of our genes. So what's the difference between here and here? What's the difference between here and here? And what is the actual sequence of the ribosomal binding site? So to do that, so we're back in DNA Master here. We're in gene 3 right here. So to do that, we have to go to the frames window we just had right here. And I'm gonna zoom in right around gene 3 here. And I'm just clicking over to the left so that gene 3 is in the middle of my window. So to do this, we have to highlight this particular gene. So to do that, just like I showed before, we click to the left of the stop codon for that gene. So this is the stop codon for gene 3. We move to the left, and I'm going to click right there. And I'm just going to keep moving to the left and clicking my mouse until it covers the whole sequence up to the start site that was picked. So this green line means that you've selected this sequence. And then, and I should mention this, all of this information is on page, I'm looking for it right now, is on page 74 in your annotation guide. So we're going to click on this button here that says RBS. And you're going to see a chart that looks like this. And right away, yes, it looks very confusing, very busy. But what this is showing is some values and some information here. So these are the different potential start codons here. So you can see GTG, 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 ATG, TTG. So remember, there are 3 possible start codons in bacteria: GTG, ATG, and TTG. So each of these here that I'm mousing over corresponds with each of these half lines right here, these black lines that go halfway up. For each of these potential start codons, it shows the distance between the start codon and an upstream Shine-Dalgarno sequence. This also shows some scores, and the scores that we're interested in here. Give me a second. The scores that we're interested in are this SD score. So this has to do with the Shine-Dalgarno sequence. How good of a sequence is it? And this Z value. So these are the two columns that we're interested in. One of these is red because this is the one, this corresponds with the start site that was predicted or called by the program. So what we want to do is we want to look at these scores. For both of these, the higher the score, the better. Now, this SD score is going to be a negative, so the higher, so minus 3.7 is a bigger number than minus 5.8. Same thing here, 2.2 is a bigger number than 1.16. So what we want to do is we want to evaluate the scores here, and this is described on page 75. I'm not going to go over it in detail here. You should definitely look at page 75. So this SD score is how well that Shine-Dalgarno sequence is. The higher the score, the better. And this is a log scale, so something that is minus 2 is 10 times better than minus 3. This Z value here takes into account a number of different things, and it takes into account all the different potential Shine-Dalgarno sequences in the genome, and I'm not going to talk about how it calculates this, but the bigger the number, the better. Anything above 2 is pretty good. And then the spacer distance, we typically want somewhere around 10. Generally say 8 to 12. So the question here is, how good is the score? Well, the start site that was chosen has a score of negative 3.7. If we look at these values, and we're only going to pick up the ones that are possible. We're not going to evaluate the start sites down here because they're not really possible, because it would be a really short open reading frame. And we're not going to evaluate the ones that are up here because it's going to pick all the ones that are between the two stop codons. This is too much of an overlap, so we're kind of interested in these, in this area here. And that would be kind of these. And if you look at these, negative 3.7 it's a pretty good score. It's not the highest score. So this score here, this start site here, has a better Z score, or has a better SD score. And this one also has a better Z score. But, so this starts at 1951. So that one would be this start site right here. It leaves a gap. So it's not the longest open reading frame. So what I'm going to do is I'm just going to leave this window open, and because I'm going to come back to these scores, and I'm going to put in my notebook here. So the question here is, does the predicted start site have a high SD and Z score? And the answer here is yes. The SD and Z scores are high, though nearby start sites do have better scores. And again, this is just for our notes to keep track of how what we're doing. So we've looked at all the data that we want to evaluate at this point. So the question is, and in your annotation guide, I'm actually going to jump to the top of page 77. The question is here, is the currently called start site for the gene the best choice? And based upon all of this data, I would say yes, the predicted start site is the best choice. And there's no way to definitively say one is better than the other. You're going to have to make a judgment call with these. But if we go back through the data, so the predicted start site, did it include all the coding potential? Yes. If there was a start site that was, if we were to go back and look at that coding potential again, and I'll pull that back up. Sorry, wrong course. So if we were to look at this gene, remember it ended around 3,400 and started at about 1800 or so, right around here. If we were to use one of these start sites that was further downstream, it wouldn't include all the coding potential. So this start site is pretty good. We would also look at, did Glimmer and GeneMark agree? Yep, they both picked the right one. Is the predicted start codon the longest possible open reading frame without excessive overlap? Yes. We'll say there's a four base pair overlap, which is very much a good thing. Does the start site match other starts? Yes. Does Starterator support it? Yes. So the only thing that doesn't support the start site completely is the SD and Z scores, and that is not a reason to throw out a start site. So based upon this, I would say conclusion, start site 1888 is the best predicted start site. Now, this is good. We have all of the information that we need in our notebook here. However, we need to put this information into DNA Master. So where do we put that? I'm going to click back on this window here, our main window, and you see in notes, the first line has this original Glimmer call. This is information from the prediction, and then there are these letters here. This is where we put our information that ultimately gets included in our final annotation file that gets sent to the database. So it's very important that we're consistent with this and we are accurate with this, because this is the official data that gets put in here. So you want to open your annotation guide to page 76. And this walks through the way in which we want to enter our data. So on page 76, you can see the first is SSC. So this stands for start site call. This is where we need to put in the actual coordinates. Now, even though this gets included in our table here, it's important to make sure we put it in here. So this is where we're going to put what the actual coordinates are. So the start site is 1888. The stop site is 3402. You can check it up here, and we're going to put it in just like that. CP stands for coding potential. So the question here is, does this start site capture the full coding potential? And we'll say, yes, start site captures full coding potential. So that's what CP stands for, coding potential. And you can always go back and look at your notes. So the coding potential, did the start site include all the coding potential? Yes. SD. This is the last thing we looked at. These were the scores. We can go back and check. Again, we have these windows that are open here. This is our SD score table, and the SD score is not the best table, or not the best score, but it's high. It's a high score. So I should mention on page 76, it talks about how to fill in this table. There's also example on page 104, and 104 talks a little more in detail about what these different abbreviations mean. So here we can include the SD score and the Z score. So I like to put SD score is minus 3.7. Z score 2.2. And it's the second highest score, more or less. It's not the highest, but it's a high score. SCS stands for Start Site Choice. Start Choice Source. Apologies. So this is asking which programs did this, which programs called this start site. So here I might put called by both Glimmer and GeneMark. So the next one is gap. So the gap, what this is asking is how close together is this gene to the previous gene. If there's a gap, we will put how many base pairs there is between them. If there's an overlap, we're going to put how much overlap there is. So here, there's an overlap of 4 base pairs. And that's important information because that gives us an idea of where the ribosome binding site might be. The next one is BLAST. So what this is asking us is, what is the best BLAST match? And you can put in even the best 2. And did they align, did the first amino acid align to the first amino acid? So if we go back to BLAST here, remember the top hit was Leo. And if we click on alignment, the first amino acid aligned to the first amino acid. Same thing with Halo, the first amino acid aligned to the first amino acid. So here, what I might write for this is, so for BLAST, GP stands for gene product 3, and this is, if you look here, it's saying that this is, or actually this is portal. So it's gonna, what we're going to say is portal protein for each of these. We'll say aligns 1-to-1 with portal protein from Leo and Halo. So this is saying that if we look at the BLAST results, we're going to see that those two align. LO stands for longest ORF. So, and again, we can always look back at our results here. So with BLAST here, we use GUO1 and Tahira, but like I said before, you can use the NIH, or this is from the Phages DB BLAST. So, and we can talk more about this in class if you're confused about that. So here, LO stands for longest ORF. So the question here is, again, is it the longest ORF without significant overlaps? We determined previously that yes, this is the longest ORF without significant overlaps. A 4 base pair overlap is very good. So we're going to say yes, longest ORF without significant overlap. So ST stands for start iterator. So the question here is, did the start iterator data support our choice of a start site? So here, what we might say is, sorry, I'm looking at my notes, that's why I'm talking slowly. So we might say start iterator data supports start site. These last two we will come back to and talk about later. These stand for function and function source. So, and you can see this on page 104. This has to do with what the role of the protein that this gene codes for is. And we will come back and look at this later. So what we've done here is we've annotated this gene. We've taken all of the data that we have, and we've determined, one, that it is likely an actual gene, and two, that it codes, and two, that its start site is most likely at this nucleotide position 1888. And now we can consider this annotated. So here I would go back to my lab notebook. I'd go to the annotation worksheet, and actually this we would do in Google Sheets. Let's open it back up. And in the Octavius Rex Google Sheet, we'd say this is for gene 3, gene call supported, yes, call start site best choice, yes. I'm actually going to change this to just start site because I want to keep track of whatever start site we call. And we'll say that's 1888. Putative function we will come back to. Annotated by me. Checked by, we'll look at this later, so we will people will be annotating some genes and some people will be checking other ones. And notes anything that was of interest here. Now this was a pretty straightforward gene. So there's not a whole lot that I would need to include here, but you will come across genes that have interesting things that are maybe difficult to annotate. This is where you would put any sort of notes. And I might just say straightforward gene, all data supported start site. So there may be times when some data supports it and some data doesn't. Now, if we go to our lab notebook here, it's going to refresh it. We've got all that data in our lab notebook. So in our lab notebook, we've got our notes on how we annotated the gene. And I would probably clean this up and make it all the same font and do it in a way that makes sense and looks nice. And then in your DNA master, you've got all that information in the notes table. The last thing we want to do is we want to save it. And you'll want to save this, you're going to want to save this on your jump drive. Give it a different name than what you saved before. So that way, at the end of each session of annotating, make sure you're giving it a new name. So I'll call this Octavius Rex annotated. And if I had already done one on the 8th, I'd say to 8-1 maybe, something like that. And save. So we've just gone through all the steps to annotate a gene. Now, obviously, it took a little while. Pretty much all of these tools are new to you. Some of them probably didn't make a whole lot of sense, like Famarator and Starterator we will go over a number of times. But now, hopefully, you've now done it once so that the next time we annotate a gene in class, you'll recognize a lot of these tools. And that's what our goal is here, to have you recognize these different tools so that when we do the next gene in class, it's not going to be completely foreign to you. If you have any questions as you're going through this during the blizzard tomorrow, I will be around. Just shoot me an email. I am happy to respond. I'll respond as quickly as possible. And you can always come by on Friday or Monday as well, because we'd like to get you guys working on this so we can really start cranking out some genes next week. Have fun in the snow tomorrow.